Hello, welcome back. We're now moving on to measures of dispersion. So what we're looking at here is how dispersed or how spread out are the observations around the mean. So this is then measuring the risk of the data set. So in the previous two classes, we were looking at the measures of central tendency, where we were measuring returns, which we can think of as the good side. So now this is now the bad side, because now we're looking at the risk of the data set. And there's many measures that we use. We can look at a couple of them. The first one we're going to look at is the range. And this is the most basic measure of dispersion. We know what this is. It's just the difference between the maximum and the minimum values in our data set. So we just take the maximum value and subtract the minimum value, and that's our range. So let's try this little example. So we've got the annual returns of Northern retail shares over the past 5 years have been this. So what is the range? So all we're going to do is find the maximum value, which is there, the 26%, and then we subtract the lowest value, which is the -9 over there. So the minus times a minus is a positive. So we can see that the range is going to be 35%. So if we want to draw it in a little, use a little line, why not? We can have a bit of fun over here. So there's our range from there to there. So we're going here from -9, that's the lowest value, up to 26% there. And then 0 would be somewhere around here, I guess. So we can see our range is then between there and there, the 35%. But there's a problem with this guy, because it's only using information from two observations, from that one, and everything else is being ignored. So we don't really use this one very much. The other ones we're going to look at on the next slides, we use much more frequently. So let's then go to the next one, which is the mean absolute deviation. So what is this? This is the average of the absolute value. So this absolute word I want to come back to in a minute. We're taking the average of the absolute values of the deviations of the individual observations from the mean. So here is our formulas, and it's not as bad as it looks, because if we just break down our formula here, the important part is we need to look at the deviations of the observations from the mean. And there, in this numerator here, we see the deviations of each observation from their mean, because remember x with the hat on, or x bar, that is the sample mean. So we take each and every observation and we subtract it from the mean of the sample, and then we add up. So there's our sigma sign. Oopsie, sorry about that. There's our sigma sign here. So then we add up all of those deviations. But now here's the important word, absolute. We take the absolute deviation. So what this means is that if we have a negative number here, we ignore the negative sign and we just make it a positive sign. And when we do the example, we'll explain that a bit more and understand why we do that. And then we're going to take the average of these deviations. So if we take the average of these deviations, we then need to divide there by n, which is the number of observations. So let's try the example and we'll clear all this up. So the returns are for top text common shares over the last 4 years have been these. So what is the mean absolute deviation of the returns? So step one, we need to see how we're deviating from the sample mean. So we need to work out what is the sample mean. So that's nice and easy. So we find that the mean of these guys there is 5%. So now what we need to do is we need to take each and every observation and see what is its deviation from this mean. So we're going to start then with the first one, which is 12, and we subtract the mean. So that's going to be there 7. And now we add up all of these deviations. The next one is 4 there minus our mean of 5. So here, this is what I was talking about. If we get a negative number here, so 4 minus 5 is -1, we ignore that minus sign and we make it a positive sign. So that's what's meant by absolute deviations. And then this one as well, -2 minus 5 is -7, but we ignore that -7, we make it a positive 7. So that's why I put these two in bold, so we can emphasize that we don't worry about the minus sign, we just make it a positive sign. So there we've got, and then the last one is the 6 there minus the 5, so it's 1. So that's our numerator, and then we divide then by the number of observations, which is we've got the 4. So just before we carry on with this, we can see why we got to turn the negatives into positives, because if we left that -1 there, and that 7 is a -7, that -1 would cancel with that +1, and that -7 would cancel with that +7, and then we'd have no deviation. So it would be meaningless. So we have to then change the sign so that we can see, how are the observations deviating around the mean. So then we see our answer comes out at 4%. Right, and then with this, and also for the next one, which is standard deviation, the higher the deviation, the higher the risk, because the higher this number is going to be, the more the observations are deviating around the mean. Right, so let's try the next one, and this is probably the most important measure of dispersion, the sample variance and the sample standard deviation. These two are related to each other. So first of all, why sample and not population? Because to work out the population variance, the population standard deviation is such a mission, because there's so much information in the population. It's normally we can't do it, or we could do it, but it would take so much effort. So that's why we rather use a sample. So what is the variance then? So it's the average of the squared deviations from the mean. So let's start off first of all with this one here, the sample variance. So as we said, we're using sample variance and not population variance, because if we use sample variance, then we're going to see how we're deviating from the sample mean. X with the hat on is or X bar is the sample mean. We're not seeing how we're deviating from the population mean. So the sample variance symbol is S squared. So here we're taking the squared deviations from the mean for each and every observation. So we take each and every observation and we subtract the mean, and then we square that deviation, and then we sum up all of those deviations again, like we did for the MAD on the previous slide. We sum up now all of these deviations, but now we take square deviation. So again, this negates the problem. If we have a negative number here, with the MAD on the previous slide, if there was a negative number, we just made it a positive number. Now, if we have a negative number here, it doesn't matter because it's going to be squared. So that gets rid of that negative problem. So variance is the average of these squared deviations from the mean. So that's why here we're going to divide now by n. But I'm sure you've spotted that we don't just divide by the number of observations. We actually divide by the number of observations less 1. Now, we're not going to go into all the technicalities of why we subtract 1, but if we read over here, when we divide by n minus 1 instead of n, we actually improve the statistical properties of the sample variance. And in statistical terms, we say the sample variance, it's an unbiased estimator of the population variance, which we'll look at later. So if we had to work out the population variance, we wouldn't actually subtract 1, and here we would have our population mean. And we'd have to take each and every observation of the population and subtract each and every observation from the population mean and square it. And that would be such a mission that we're not going to worry about it. We only have to worry about sample variance. Right, so now we're going on to standard deviation. So what is this now? It is actually the square root of the variance above here. So we're just going to take the square root of what we have above. And this standard deviation, it is actually expressed in the same unit of measurement as the observations are. Because when we take the square root of this here, because let's say we were working in percentages, this answer would come out in percentage squared. But when we take now the square root, we return the values to the original unit of measurement. We would then go back to percentages again. And this makes standard deviation much easier to interpret than variance. So that's why we actually prefer standard deviation. So as we go through the curriculum, when we want to measure our dispersion or risk, we normally use standard deviation. It's the most common measure we use, and not variance, because we now back to the same units as the underlying data is in. So let's just take this little example to explain this. Let's say we've got a sample and all the values are in dollars. If we had to now interpret standard deviation, the standard deviation then is also going to be in dollars, which is much easier to understand because the variance would be in what? The variance would come out in dollars squared. So that's hard to understand what a dollar squared is, but dollars is much easier to understand. So that's why we're going to rather use standard deviation. That's why it's much more common. And we're going to, what I've said there, we're going to apply that to this example over here. So we've got the returns for top tech shares. Okay, this is the same information as we had for the mean absolute deviation example, but now they want us to work out the sample variance and the standard deviation. So again, to step one, we need to work out the sample mean, which we did already. We know it's 5%. So so S squared now, that is the variance. So for the variance, we've got to take each and every observation's deviation from the mean squared. So we take 12 minus 5 squared, and then 4 minus 5 squared, and then minus 2 minus 5 squared, and then 6 minus 5 squared. So then we can see how these are the deviations in the numerator. So we can see that we've got there 12 minus 5 is 7, 7 squared is 49. So you can see, like, for example, let's take this one here. Minus 2 minus 5 is minus 7 squared is 49. So that's if we square, then we get a positive number. So if we didn't square, you know, the negatives again would cancel out the positives, and we would have no deviation. So that's why we square. And remember for the denominator, to get the average deviation, we actually subtract 1 for the reason we spoke about on the previous slide. So our variance comes out at 33.33, but there's a problem with the variance, like we were saying on the previous slide. This is now in percentage squared, which is actually hard to understand what percentage squared is, because we don't work in percentage squared, we work in percentages. So if we now take S, which is the standard deviation, we're going to take the standard deviation is the square root of the variance there, and that now we're coming back to percentages again, and it's now in the same units as our underlying data is there in percentages. So the standard deviation uses the same units as our observations are. So that's great, and that's why we prefer, as I was saying, that's why we prefer standard deviation to variance. So as with the MAD, the higher this number is, the higher the risk, because the higher this number is, the more the more the observations are deviating around the mean. So the higher the risk, the higher number, the higher the risk. The lower this number is, the lower the risk, because the less the observations are deviating around the mean. Great. And now we're going on to downside deviation. So the variance and standard deviation that we just did, they incorporate returns like we saw that are above and below the mean. But we normally only worried about downside risk. That's the important risk. So for example, returns below the mean or some specified minimum target return. So this target downside deviation, or some people call it the target semi-deviation, what this is a measure of dispersion of the observations only below our target, whatever our target that we set. So we're only looking at our dispersions below a certain target. So this formula looks rather bad, but it's not really. It's very similar to the standard deviation that we just been through. So that we're talking here now about the target downside deviation. So what we need to do is take each and every observation and now see how it's deviating not from our sample mean anymore, but B, which is our target. So we're seeing how is each and every observation deviating from the target, but we're only going to take the observations that are less than or equal to our target. So any observation that is higher than our target, we just ignore it. We don't include it in our calculations. And we when we come here, I'm going to actually mention something else, that we don't actually have to worry about values, observations that are equal to our target. And we'll see why also when we do our example. So anyway, once we've done all our deviations in the numerator and squared them and added them all up, we then again, we divide by the same thing, the number of observations less 1, and then we take the square root so we can get the deviation and not the variance. Right. So as we were saying, we only take into considerations the observations that are below the target, because and as I was saying, we don't have to worry about observations that are equal to the target, because let's say our target is 2. Our target is 2 there, and we've got an observation that is also 2. Well, 2 minus 2 is 0. 0 squared is 0, so it's not going to have an effect. So if it's equal to, we don't have to worry about it. So only have to worry about observations that are below our target. So then what do? As I was saying, we take the sum of these squared negative deviations. The deviations will be negative because they're below the target. So we're going to square them. And then once we've squared all of them and added them all up, we're going to divide that sum by, again, our number of observations less 1. And once we've done all of that, we take the square root. So it sounds a lot worse than it is. And it's very similar to what we've just been through. And just before we do the example, I've just forgot to mention something, that when we do standard deviation, you can just plug the numbers into your calculator and then hit the standard deviation button, and will give us the answer. But I wanted to go through the whole thing because remember the exam, it's quite conceptual. So it's unlikely they're going to ask us just to plug numbers in the calculator. They want us to understand what this is, right? So but if you don't know, how, but just in case there is one on the exam where they ask us to calculate it, we don't want to get it wrong, and we don't want to have to go through all of this if it is on the exam. So just make sure you know how to do it on your calculator. In the calculator tutorials we sent you, we did show you how to plug the numbers into the calculator and then just hit your standard deviation button. It is very, very easy. Okay, so let's continue then to do an example of downside deviation, and we're going to see it's not so bad. So I just want to, this thing's just in the way for me. It might be blocking you now, but I've moved this little camera thing here a bit so I can see the numbers. So it says the returns for a portfolio over the past 6 months have been, I'm just going to read them out because this camera thing might be blocking your numbers a bit. Hopefully you've got a hard copy in front of you though. So it's the returns over the past 6 months have been 3, -1, 2, 4, 0, and 1%. So they want us to work out what is the target downside deviation or the target semi-deviation. When the target return is A, we've got to do 2%, and then after that, we've got to do a target of 3%. Then they want us to compare these to our sample standard deviation. So let's get going then. First of all, with a 2% target. So what do we need to do? We only need to take into account the observations that are less than 2%. So the first one is 3%, so we ignore that one. We don't have to worry about this one. Okay, the next one is -1, so that's less than 2. So we're going to take that -1 minus 2 squared there. And the next one is 4, so 4 is more than 2, so we're going to ignore that one. The next one is 0. And so 0 then is less than 2, so we're going to take 0 minus 2 squared. And the next one is 1. So the next one is 1, that is less than 2. So we're going to take that one, 1 minus 2 squared. So if we then go through all of our deviations in the numerator and divide by the number of observations minus 1, which is 5, we get an answer of 2.8, but that is now going to be in, again, percentage squared. We can almost think like that as the variance. But if we want to work out our deviation, what do? We take the square root of that and we get 1.67, and there we back now to our same as our underlying units, our percentages. Right, so that is the downside deviation for a 2% target. Now, what about a 3% target? Okay, so the first one is 3%. So that one we don't have to worry about. And as I was saying, if the observation is the same as our target now is 3%, we could put it in, but 3 minus 3 is 0, and 0 squared is 0. So we don't have to worry about anything that's the same. That 3% is the same as our target, so we're not going to worry about it. And then the next one is minus 1. So that is below our target of, that minus 1 is below our target of 3. So we're going to take that one into account. That 2% now is also below our target of 3. So we're going to take that one into account. And then the 4 is above. So we're going to ignore the 4. And the next one is 0. That's below. So we're going to take the 0. And the 1 is below our target as well. So if we work that all out, we see it comes to 6, and that's again in percentage squared. So we take the square root of that, and we come out at 2.45, and that's going to be our downside deviation. So this block here in the middle, I think, is very important, because as I was saying, they love to ask these conceptual type questions on the exam. So we can see if the target return is higher, like this, there we had a 3% target return there versus a 2% target return. So if the target return is higher, the deviations are larger. So let's stop there. So let's take the deviations for the return here of the minus 1. So the minus 1, it was below minus 2, and it was below our return, target return there of 3. So minus 1 minus 2 is minus 3. Minus 3 squared is 9. Okay, what about this side? Here, our target is 3%. So the minus 1 minus 3 is minus 4. Minus 4 squared is 16. So you see here, the deviations are now larger. So for example, with that observation there of the minus 1, the deviation is larger. And so not only are the deviations larger, they're also more deviations that are below our target if the target return is higher. So for example, for this 2%, we didn't take it into account for this 2% target over here, because it was the same. If we did take the 2 minus 2 is 0, then there's no difference. But now we are taking this deviation into account, because 2 is below 3, so we need to incorporate it when we do our 3% target. So here's an example of more of here. There are more deviations now below the target. So we got larger deviations here, and we got more deviations below the target. So we're going to get a higher numerator here if we've got a higher target return. So this means that if the target return is higher, the semi-deviation is going to be larger. Okay, so I just wanted to highlight that these, as I said, these kind of conceptual things are very important. So if we compare it to the standard deviation, you guys can just do the standard deviation here like we've done before, just double check. You can see the standard deviation comes out at 1.87, and we can see that the standard deviation in this example, it's above our target downside deviation when we got a 2% target, but it's below the target downside deviation when we got a 3% target. And again, for this standard deviation, you can just plug these numbers into your calculator and hit the standard deviation button, and you're going to get your answer there of the 1.87%. Great. And this is the last thing we need to look at in this class, which is the coefficient of variation. So what we've just been through are the measures of dispersion. And in the previous two classes, remember, we did the measures of central tendency. So this is a great little ratio, the CV ratio, because we're now combining the two together. So it's a ratio then of the standard deviation, which we've just been through, which remember we said it's the risk. So it's a ratio of our risk of a set of observations to their mean value. So our mean is our most common measure of central tendency. So now we're combining both of them together, which is fantastic. So what does this thing then measure? It measures the amount of risk, which is our standard deviation, per unit of mean return. So we're taking both into account, not just risk and return, we're taking both into account in a little ratio. So an example where they like to use this is, you may have heard in South Africa, we've got these things called the Raging Bull Awards every year, where they give out awards to investment managers who've performed the best in the industry, who's had the best funds. And so they don't just take into account, what return did the fund manager do. They also take into account how much risk was taken to generate that return. So we can see here that I've put a little box here. The lower the CV, the better. Why is that? Because it's the amount of risk, which is standard deviation in the numerator. S is our standard deviation per unit of mean return. And our mean return is our X bar, our sample mean. So what do we want? We want, as we were saying earlier a few slides ago, we want the risk, the standard deviation, to be as low as possible, because then we are deviating the least. The lower the standard deviation, the less we are deviating around the mean. So we want a low numerator there. And what do we want as far as returns go? Of course, we want our returns to be as high as possible. So if we've got a low numerator and a high denominator, that's going to give us a low ratio. And that is what we want. And so we're not so good with ratios yet because we haven't done financial reporting. But once we've done our financial reporting, or not even all of it, but as we've done it after a few classes, we're going to become experts with ratios. So if you're a little bit confused about, how this ratio is working, don't stress, because we're all going to become experts with it. So let's just do this example quickly. So we've got the equity growth mutual fund of best investments has had an annual mean return of 11% over the past 5 years with standard deviation of 6%. And the equity growth mutual fund of state investments, they have had an annual mean return of 13% over the past 5 years, standard deviation of 9%. So let's work out the CVs for these two funds. So for best investments, we got to take the standard deviation there, 6, and we divide by the mean return of 11. So it's going to be 0.54. And for state investments, we take their standard deviation there, 9, and we divide by their standard deviation. We take the standard deviation there of 9, and we divide by their mean return of 13. So theirs is 0.69. So who is better? Is best investment better, or is state investments better? Well, best investments is lower, so they better. The lower the CV, the better. So the best investments, they have got a better CV. That's why they're best investments. just kidding. Because they have got less risk per unit of return, because it's risk there per unit of return, right? And they've got less risk per unit of return. So they are the best. And then I just made a note here that we can see that the CV, it's got no units. It's, in other words, it's what they call scale free. Why? Because both our standard deviation and our sample mean, they're both in percent. So for example, there's the mean return 11%, and we said standard deviation is in the same units as our underlying data, also in percent. So we would have if we wanted to, we could put a percentage sign there and a percentage sign there. And if we did that, once we divide, the two would cancel each other out. So that's why we end up with a number here that's got no units. Great. So that's the end then of that class. And we'll see you guys in the next one. Hello, it's Tim here again. I hope you enjoyed the class and found it beneficial. We have some classes available for free on YouTube, but we have classes for the entire curriculum. The classes that are not on YouTube can be purchased from us. If you'd like to purchase the classes, please contact us for the pricing, and I've put our contact details over here. You can purchase all the classes or certain readings that you would like. When you purchase the classes, we provide you with the slides and our notes. I've assisted hundreds of candidates pass CFA exams, and I look forward to also helping you through the CFA program. I've put in 2 testimonials in the slide over here, and we also have a testimonials page on our website that you can review. I look forward to seeing you soon, and all the best.